we'll call that beta 2. Then there's energy in machines. So the machines include things like tractors or combines. Energy includes things like electricity for running pumps for irrigation. You can think of a lot of other things energy might be used for, but that might be the big one, though. So energy is raised to the beta 3 here. And then finally, there's chemicals and seeds. So chemicals, you should be thinking about fertilizers and pesticide bundles for the most part. And of course, seeds is self-explanatory. I'll call that seeds. And that's raised to the beta 4. Okay, so that's the production function that Fugly is imagining that farmers are operating. He's going to allow this technological parameter to vary over time, and he's going to allow these share parameters to vary depending on where the agriculture is being conducted. Bless you. So in India, for example, just I'll show you this entire column. I've broken up this table so that the top 4 countries, India, Indonesia, China, and Brazil, are developing countries. They're poor countries. Notice labor share in these countries is pretty large compared to the bottom panel, where we have developed, richer countries, higher income countries. So that's not necessarily. So what that tells us right off the bat is that in India, 46% of the costs of farmers' costs go to paying people to grow stuff. That's labor share. The share in rich countries is, or in the U.S. and the UK at least, is quite a bit lower. And it's quite low in the U.S. In the U.S., labor share is less than half what it is in India, at 20%. And Japan is just a little bit below the developing countries at 0.39%, and the UK is somewhere in between. Now, that difference in labor share, I would say, probably isn't a consequence of the countries being rich or poor. That's not what's driving the difference. The difference here probably has more to do with the scale of agriculture and the nature of agricultural holdings. So a characteristic of the U.S. in particular is that a large proportion of output is grown on large-scale farms, large acres that are flat and don't have lots of rocks and mountains. In India, in contrast, the average holding is less than a single hectare. And so that lends itself less to mechanization. So to get a tractor on such a small plot is not as useful to do so. Japan's another example of a place that has small-scale agriculture. Again, given holdings tend to be quite small. Is there a question back there? No? Yes?
So we haven't talked about labor rates.
Yeah, there's no prices here yet. Is that what you mean? There's no, yeah, we haven't used any wages. The answer is no in this case. That's a consequence of our assumption of constant returns to scale, and it's true for this Cobb-Douglas production function. I'll come back to that later maybe, but maybe I'll remind you of something that's true for the Cobb-Douglas utility functions we worked with. So remember there, when we wrote down a utility function that looked like u of x1, x2 equal to alpha log x1 plus 1 minus alpha log x2. You'll recall that we wound up with an expression that said that things like P1x1, that is expenditures on the first consumption good, were just equal to alpha. That was true for these Cobb-Douglas utility functions. Something analogous is true for these Cobb-Douglas production functions. So a profit-maximizing farmer who faces different prices for this stuff is going to change his demand for labor and for seeds or energy or whatever depending on prices, but he's going to do so in a way that his total expenditures on that thing are going to remain constant. So what's important here is that these things are measured in expenditures on land, expenditures on feed, and so on. So that the shares are taken to be constant here, and that implies that expenditures are constant. It doesn't mean that demand doesn't vary with prices, but it means it varies exactly inversely. So total expenditures remain constant. When prices double, demand for the input halves. No, I'm sorry. So we want to measure in expenditures, but it doesn't matter whether those are in expenditures or in quantities here. Expenditures are going to wind up being constant if these farmers are solving a profit maximization problem. That's the consequence here. In the same way that consumers have constant expenditure shares with Cobb-Douglas utility functions. Okay. All right, so here's some shares, and there's an interesting difference in labor shares. There's other interesting differences here I'll point out as well. You can see that for the U.S., U.S. has the largest livestock share, because we're a very large livestock, right? Maybe I should say it's a consequence we're a large livestock producer. I'm not sure what it is about the U.S. technology that makes us good at producing livestock. Energy machines, you can see these things are pretty small for the really poor countries here, for India and Indonesia. Energy machine expenditures are tiny. For Brazil, they're larger. Brazil also has large-scale agriculture, so we can have more tractors kicking around. Let's see. Notice again, I think reflects the small holdings in Japan. It's 5% for machines is the share. Chemicals and seed, again, we see some pretty big differences. Indonesia have rather small shares. The U.S. again has by far the largest share. So you can see what's happening to the U.S. compared to India, for example, is we're substituting chemicals and seed and machines for labor, and those are the big differences there across those two lines. Yeah. Oh, dear, that's a sign that I made a typo, I think. Yeah, all these shares should add up to 1, in fact. I don't know what the culprit is. Is it really 0.39.2? Okay, so I'll have to check. My typing isn't necessarily perfect. I suspect a data entry error first if that addition is correct. Okay, all right. So anyway, we're going to use these. We can use these things then to construct. What Fugly does is he takes these individual countries, weights them by the total amount of their agricultural produce as a share of world produce, and after that weighting comes up with shares for the world. So worldwide, the costs of producing agricultural output, 35% of the costs have to do with labor, 21% with land, basically, livestock and feed, 23%, 10% to tractors and so on, and 10% to chemical inputs and seed. It's kind of interesting. What that means is we have a choice here. If we wanted to think about modeling world agriculture, one thing we could do is just take these numbers and plug them in. We could say that world agricultural output is equal to some A. We haven't said what A is yet, but it'd be equal to labor raised to the 0.35, land raised to the 0.21, and so on. If we wanted to model developing country agriculture, or agriculture in India, say, we'd use different shares. We'd use the labor share of 0.46, we'd use a land share of 0.23, and so on. All right. Any questions about the interpretation here? Yeah, you can see it's a nice thing. It's another nice feature of Cobb-Douglas production functions. They mathematically nicely behave. They're also easy to match up with data because of the interpretation of these parameters as being related to input expenditure shares. Yeah. So if this specification of the production function, the question is, do these alphas and betas, do these things depend on the supply of land and the other inputs or not? And the answer is, there's two qualifications. If this is the right specification of technology, or basically if they're constant returns to scale, and if agriculture in the country is competitive, then these shares will not depend on prices, and hence won't depend on supply. That's a theorem due to Solot, who I mentioned earlier. Okay. All right, so I want to go ahead and so I've got these shares. I can model these production functions. That's nice. I'll say also that if you're interested in estimating these things without this kind of data, one way to do it is just to take this expression and take logs. So if you had data, and these are data you can get by the way, you could write the log of y is equal to the log of a plus alpha times the log of L plus beta 1 times the log of land. I'll go ahead and write it out, plus beta 2 log of feed plus beta 3 log of energy and plus beta 4 log of seeds. Now, for those of you who know have some familiarity with regressions, I think you've taken E118 or have seen it in stats, this should look a little suggestive. So in particular, what you can do is imagine getting data on this, getting data on land, taking logs, getting data on here, all these circled things are things you can get data on, and then estimating a regression. So what you don't have data on is this thing. And so this is actually why it's called a solar residual. It's because if you estimate this regression, this thing winds up being the error term. So it's going to capture differences in productivity that aren't reflected in differences in input use, whether it's across farms or countries or whatever. So we can compute the logarithm of A as a residual in a regression of this form. Okay, so Fugly did this exercise, or one very close to it, and came up with the following numbers. He was able to, he had data on output for all these countries, data on variable input use, which changes over time, of course, and so he was able to estimate something like this and come up with a time series of data on output Y and on this residual A. This is for the globe. These are using the global agricultural estimates. So we're using the shares here at the bottom line. Okay, so when you do that, here's the simple data. They're organized decade by decade because the availability of data for these different areas, you don't get it every year. So anyway, so average, the way to read this is all in terms of growth. So from 1970 to 1979, total output grew at a rate of 2.23% per year. From 1980 to 1989, it grew at a global agricultural output grew at a rate of 2.13%, and so on. Of that increase in agricultural output growth, the A, so I think this is an improvement in agricultural technology, a Higgs-neutral improvement in technology, increased at 0.6% per year from 1970 to 1979, increased at 0.9% per year from during the 80s. The rate of increase got faster in the 90s, increased to 1.6% per year and 1.55%. So you can see the difference is made. So two things are going on. One thing is that total input use is growing. Farmers are producing more food, and it's increasing. 2% annual rate of growth is considerable if you do it every year. That increase in agricultural output comes from increases in input use, but then also increases in improvements in technology. And so let me, using those data, show you just a picture of those growth facts. Here. Yeah, there it is. So this is a figure from Fugly's paper. And it really just reports the numbers I was showing you, basically. But so the box thing, this thing on top, is total annual growth rates in agriculture. Now, remember, these are growth rates every year, and every year they're positive. So if we were to grow total growth, we'd see this, this thing that's increasing at an exponential rate still. But anyways, these are growth rates. That growth rate has maybe fallen a little bit over the last, the last 50 years. But it's, during the last 20 years, 25 years, it's increased a little bit. So this is agricultural growth. That change in total agricultural output depends on two things. One is changes in inputs. Those are these triangle guys. Now, input use was growing at a high rate in the 60s. These high rates of input growth have to do with the Green Revolution, by the way. So there are high rates of input use growth in the 60s, but it's fallen very steadily up until the early 90s, and then it kind of bottomed out here. So the rate of growth at which people are turning new land to agriculture or more labor going to agriculture or these other inputs has fallen over time. That's been approximately compensated by an increase in the rate of growth in A. So agricultural technology, the productivity of these inputs has been steadily increasing over time. If you leave out this thing, it's been increasing at an increase, more or less an increasing rate, in fact, over the last 50 years. So in the early 60s, people were very worried about widespread famines and how we're going to feed the planet. The answer we've had so far, and that's something you might worry about in the future as well, but the answer we've had over the last 50 years has been twofold. It's been, well, we're going to improve agricultural technology in a way which allows us to continue to feed the planet, while at the same time reducing the rate at which we have to use resources like other resources and inputs like labor and land, chemical inputs and so on, in order to provide that agricultural productivity growth. Okay, so with that, let me stop. Are there any questions before we leave? Okay, good. Thank you.